So first topic here is going to be on the periodic table. The periodic table was developed by a Russian scientist by the name of Dmitry Mendeleev. Basically, he was interested in the properties of elements, and he had noticed that several of the properties of elements started repeating as you sort of went up along with respect to atomic mass. That if you basically rank the elements in terms of atomic mass, that their properties started repeating as you'd go 8 elements, and then you get something that was similar to the element that was 8 elements ago, and then 8 more elements, you get another element that's similar to the elements that was the element that was 8 elements before that. And so he set aside himself to try to figure out a pattern, a way to write out all the elements so that all of their properties would repeat. And basically, this idea that every so often is if you rank the elements by their atomic mass, that you will basically see repeating characteristics of those elements. It's called the periodic law. And so he used this law and was able to basically create what he called a periodic table. And if you look over on your right, this actually is Mendeleev's periodic table in Russian, because he's Russian. It is oriented different than ours. If you sort of look right over here, you can sort of see there's hydrogen right there. It's sort of not at the top left. It's actually sort of, so this periodic table has been rotated 90 degrees and then flipped. So you can then sort of see we have, boron, carbon, nitrogen, oxygen, fluorine coming across there. It's sort of backwards from ours. But this is what he came up with. And it turned out that this periodic table did explain or did show the repeating characteristics of the elements, and but more specifically, it actually gave the ability to show a prediction. If you look carefully, you will see, and it may be difficult to see on your screen, but there are 2 elements that are right here, 68 and 70. If you notice, they have question marks in front of them. And the reason why is because in order to make this periodic table work, Mendeleev basically said, I've got some gaps. I've got some areas where we don't know any elements that would fit these characteristics, but the pattern says there should be elements here. And so he published this periodic table, and actually it turned out that once he had done that, within a few years, is that one of these 2 elements was discovered, and later on the other one was. And so this showed that this periodic table had to be correct, because he correctly was able to predict elements with certain properties that hadn't even been discovered yet. And so this is Mendeleev's periodic table. The modern periodic table is somewhat different. Obviously, orientation makes it a little bit different right there. But overall, the main key about it is that while Mendeleev ranked his periodic table with respect to atomic mass, the periodic table that we use is ranked with respect to atomic number, that is the number of protons, because there are a few elements that don't quite match up if you do it by atomic mass. And so to look at the modern periodic table, let's take a look at what we've got here. This is once again an example of it. You've seen this before. Periodic table is categorized into periods and groups, and then also families. So periods is the reason why they call it the periodic table. A period is basically a set of elements that then will repeat a pattern of characteristics with another set of elements. And so effectively, in terms of what really is going on here, what a period is a period is basically the horizontal rows that you see on a periodic table. So you can sort of see we've got period over here, and so the first period would be going across here, hydrogen and helium. The second period would be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and so on and so forth. The 5th period would be going across right here. And so that sort of tells you about periods. So periods are just numbered, so the first period, second period, third period, and so on and so forth. It simply just tells you that that means that lithium is going to have a similar characteristic to sodium, second, third period, then potassium, rubidium, cesium, francium. These all have similar characteristics. And in the same way, beryllium, magnesium, calcium, strontium all have the same characteristics. They repeat as it goes from one period to the next. So periods are horizontal rows going across a periodic table. Next one here would be groups. If a period is the horizontal row, the group is going to be the vertical column. And so group 1 would be this setter right here. Groups always have similar properties. And so lithium, sodium, potassium, rubidium are all very similar. Beryllium, magnesium, calcium, strontium, period 2 are the same way. Same thing for, if I take 18, helium, neon, argon, that particular group. And so groups are your, are your vertical columns, and so they are numbered 1 through 18. Sometimes you will see an alternate way of writing these out, in which basically that we have 1A, then we have 2A, and then the ones all in the middle here that are in the D block are all going to be B's, and then we have 3A right here, and going across all the way up until you get to 8A for this final one. That's the older system of writing out groups. You'll see periodic tables that have both of these on here. It's probably simpler to go ahead and just use the group numbers 1 through 18. That is the modern way of doing that, of writing those out. But just be aware that sometimes the groups are written in that sense. The next topic that we have here are families. Now, we said that within groups is that what we saw is that groups all have the same characteristics. And so we could go and we could take, say, these guys right here, these elements, and they have the same characteristics. And so in a lot of ways we can talk of them as being not just a group but as a family. Now, groups are sort of defined by what number they have. And so we said that, it's group number 1 is what that is. But a family will typically have another name. It'll have a name that actually describes what the elements are like. And so these are listed in the box that's sort of in the middle right up here, right up in there. So in this case right here, group 1, that particular family is called the alkali metals. And you can sort of see that that's what it's got listed right here for alkali metals right up there. And so the alkali metals are these ones that are in group 1. They are called alkali. The word alkali comes from a root in Greek which basically means salt form, or means basic, like you said, of an acid or a base, because the alkali metals are typically involved in the creation of bases. And so those are the alkali metals. The next set that we have here are going to be sort of right next door to them, which are going to be in group 2. And those guys are the alkaline metals, or sometimes called the alkaline earth metals. So that's them right there, sort of the blue dot there. And so alkaline earth metals are those right there. The next ones that we will talk about here are going to be way over here. These are our red ones that are in group 17. Those guys are the halogens. The halogens, this is the one that comes from the Greek word halos, meaning salt. Gen is like the word genesis, to create. And so these would be salt creators or salt formers. The reason why is because most salts you run into have one of the halogens involved. And so those are your halogens right there. The next family we have here are these at the far end right here, group 18. Those are the noble gases. The noble gases are called noble gases because they generally don't react with anything. They very rarely ever react and form compounds with other elements, and so they're considered to be noble because, like nobility, they don't deal with the commoners. They are off by themselves, and so they're called the noble gases because, well, as far as elements are concerned, they're pretty stuck up. So those are the noble gases in group 18. We have a couple other types of families that we have here. One is going to be that most all the things you see in the D block, right in the middle, and I will include a couple here that actually don't involve, those are just the purple ones, the ones that really we're interested in here. These are called the transition metals. These transition metals, because of the fact that they do transition from the groups 1 and 2, from your alkalis and your alkaline earth metals over to the rest of the periodic table over here on the right. And so those are the transition metals, and we'll talk about what metals are in just a second. So that's one set of ones we have here. The next ones are going to be the two green ones we saw before, and these two segments of elements that sit at the bottom. Now, as a whole, these are called the rare earth elements. For the most part, they are not very common. You don't find them on Earth very often. You've probably never run around and picked up a chunk of uranium that's sitting on the ground there, because these are not very common elements. In fact, some of them aren't really even like the ones that are up here, are almost entirely man-made, and you won't find them on Earth at all. So they are considered to be the rare earth elements. Those two rare earth elements, they come into two types. The first type are the ones that are at the top of the F block right here. These guys right here, those are the lanthanides, as it says right there, named after lanthanum, the very first one. Technically that should be down below on the bottom section. And the next one down here are the actinides. And so the actinides, named after actinium, which is their first element that starts them off. And so those are just some naming things of different families that we see on the periodic table. Next thing we'll talk about here are metals, nonmetals, and metalloids. So metals are first here. So what is a metal? Well, a metal is an element that basically shares its electrons fairly freely. Is that it gives them away to other elements, that they're able to move back and forth between elements fairly easily, and they form compounds with those. And what that means is, it means one, they conduct electricity very well because they can move their electrons back and forth. It means two, that they conduct heat very well. There are some other properties they have as well. Sometimes you'll hear about malleability or ductility, these abilities to flatten or stretch out into wire, but the main ones deal with basically their freedom of their electrons. Metals, for the most part, tend to sit on the left side of the periodic table. The dividing line between metals and nonmetals is sort of a stair-step line. You'll see it on certain periodic tables. It'll sort of look usually a little bit like this. I'll sort of draw it out like that. And so that's your stair-step line, and that really isn't very viewable at all. Let me see if I can get a better color on that. I'll use red. There we are. There's a stair-step line. So this is typically what is considered to be the dividing line between metals and nonmetals, with metals over here and nonmetals over here. And that can't be read at all. But you get the basic idea. So metals are over on the left side, nonmetals on the right side. And the dividing line roughly runs along that set of that stair-step line that I drew a little bit earlier. And so there is one exception to this, and that is hydrogen. Hydrogen sometimes acts like a nonmetal, sometimes acts like a metal. So it's sort of halfway between. It's on the metal side of the line, but it does have some characteristics like being a gas that make it closer to the nonmetal side. But sometimes it does give away its electrons pretty freely, so sometimes it acts like a metal. And in fact, if you cool it down to really, really low temperatures, then hydrogen acts very much like a metal. But you just fill up a balloon here, it really doesn't act much like a metal there. So it's sort of the halfway one right there. So metals on your left, nonmetals above the stair-step line to your right. There are a few elements that do show characteristics of both, and those are called the metalloids. And the metalloids are the ones that are in yellow right over here. And so they generally tend to follow that stair-step line. And so if you take a look when we drew that stair-step line out before, you could see that for the most part they're either just right above it or right below it. And so these are ones that have some characteristics of metals, some characteristics of nonmetals. Things like, say, silicon. That's one of the reasons why silicon is used in computer chips, because it sometimes acts like a metal, sometimes like a nonmetal. So sometimes it can conduct well, sometimes it can't. And so that lets you turn on electricity and turn on currents, which at certain times, which then basically allow it to basically work as a computer chip material. So these are your metalloids that sit right there. The root oid means like, but not exactly. Like I said, an android is basically a machine which is like a man. Andros is the word for man. And so a metalloid would be like that. If you made a robot that looked like a cat, it would be a pheloid, because feline is for cat, oid is like. So metalloids are elements that are like metals. Sometimes they are considered to be metals, like germanium and antimony and polonium. Sometimes they are not, like boron and silicon and arsenic and tellurium. And so those are your metals and your metalloids.